welcome to WOW 11. Today's webinar, using HD technologies for process optimization and conditioning monitoring in smart mines, presented by Hakan Hedlund, is brought to you by Mobius Connect's Week of Webinar series. I'm Alexa Gruber, the media specialist for Mobius Connect, and I'll be your moderator for today's session. This webinar is being recorded, and later you will be emailed a link with access to the on-demand version of this webinar. If anyone has any questions throughout the webinar, you may type them in the Q&A panel on your screen. And at the end of this session, Hakan will reach out to you after to make sure your questions are answered. All right, Hakan, I'm going to go ahead and pass the presentation over to you now.
Hello, and thank you very much for giving me the opportunity to do this webinar. The purpose of this presentation is to give examples of how to use online systems based on the HD technology for both condition monitoring and process optimization. Short introduction of myself. My name is Hakan Hedlund. I've been stationed here in SBM headquarters in Strängnäs, Sweden, and I've been working here with condition monitoring for about 35 years, or actually 37 years. I'm CAD 3 certified, and I've been involved in sales, product development, area sales manager, and a lot of trainings. Nowadays, I'm focusing on introducing the concept of combining condition monitoring and process optimizations to our international sales and support organizations. And this presentation is more like a teaser. There will be designated webinars, presentations with in-depth descriptions on how to optimize the toe position in tumbling mills, optimizing the throughput in vibrating screens, and other similar presentations. So that's a short intro to this presentation. We have traditionally focused on condition monitoring of machines, where we have detecting faults like bearing faults, gear faults, misalignment, unbalance, lubrication issues, and other rotating parts and faults. But with the HD technology, it makes it possible to pick up crisp and clear signals generated by the process, such as filling grade in tumbling mills, toe position, charge composition in tumbling mills, elliptical movement in vibrating screens, lining conditions, pulsation in slurry pumps, and cavitations, and other types of wear of critical machine parts. So, as you can see, nowadays, these goes hand in hand. So we work in parallel with these two things, with process optimization and condition monitoring. Now we use one system for both condition monitoring and process optimization. So if you look on this tumbling mill, for example, we typically install an online system on the machine, and we have our traditional software for condition monitoring, where we look at trend graphs, color spectrum overviews, spectrums, and so on. But nowadays, we also export smart data through API, like toe position, charge composition, to mill control system. So those systems can control the running of, for example, a tumbling mill. And for a tumbling mill, it's very important to keep track of the toe position, because that is related to the filling grade of the mill. So that is one thing, that the mill control system adjusts the input and output feed of the mill to have a correct toe position. And then we have dashboard that the operators can look at, so they can identify a sweet spot where the toe position should be. So that is a short introduction and an overview over how we use our online system, both for condition monitoring and process optimization. Here we have a overview over a typical mine. Above here we have machines typically that you will find in the mining and excavating. And down here we have typical machines that you will find in the concentrator plant. There are crushers, hoists, conveyor belts, tumbling mills, slurry pumps, screens, and flotation cells, belt filters, vacuum pumps, and so on. And we will look into a few of those. We have examples on all of these, but for now we will just look at 4 or 5 of them. And I think we start with the tumbling mills. And here we can take 2 routes. One is the toe position monitoring, and the other one is condition monitoring. But remember, we do this with the same system, so it's not 2 different systems, it's one system doing both. Okay, here we have a picture of a autogenous mill, and we place one vibration transducer on the inlet and one on the outlet. And with these 2 sensors, it's possible to measure the toe position in both ends. And this simulation illustrates what's happening inside one of these mills. You have the toe, you have the charge, the lifters, the shoulder of the charge. And the solution that we measure the toe position with very high resolution using vibration technology. Too much ore in the mill will be shown as a high toe position, while too little ore will be shown as a low toe position. A fill grade with too much ore leads to inefficient grinding and a potential overload situation. In that case, the inlet feed is stopped and the mill grinds out, resulting in losses in the throughput. And too little ore in the mill results in excessive wear of the liner and lifters bars inside the mill. And here we have some examples of fault modes in tumbling mills. This is typically how it should look like, that you have a efficient grinding in the mill. But for some reason, you can have volumetric overload, you can have freewheeling, and you can have slurry pooling. And this is, of course, something you want to avoid because it can lead to problems, mechanical problems, but also very inefficient grinding of the ore. And if the toe position is too low, it will lead to excessive liner and lifter wear, but it's also very inefficient grinding because the ore will fall down on the rubber lining and lifters, and that's not very efficient. So this is something you want to avoid. The forces generated by the impact between the lifters and the charge is picked up by a very sensitive vibration transducers. So every time the lifter hits the charge, a signal will be generated, or force will be generated, and that is picked up by the vibration transducer, and that will generate a signal that looks something like this. And we do synchronous time averaging to have a very crisp and clear signal. Adding a tachometer signal, we will get both the amplitude and the phase, and then we plot that in a polar plot. So in this case, this green dot represents the position of the toe in this case. And in this, all the small blue dots here are measurements. So there are many thousands of measurements that you can see here in this polar plot. So if the charge of the toe position changes, this point will also move away like this, up and down. I will show you some examples. And here is one way of trying to explain how the position in this polar plot, these results, how it's moving in this kind of swirl when the mill is has a very high toe position. And if you start this animation, you will see that the toe position will go down like this. And the reading here will go like this. And then when the mill is empty, the amplitude will be very low because there is no forces generated between the ore and the lifters. So if we repeat that one, so here we have a very high toe position. And if you close the inlet and let the mill run, it will be less and less ore in the mill. And at a certain point here, it will be empty, and then there will be very little vibration caused by the interference between the ore and the lifters. And here's a short summary of this swirl, how it's interpreted. And you could say that when the results move in this direction, we have an increased toe position. If it goes down, it's decreasing. But at the same time, we also have the density affecting here. So the amplitude is related to the density of the ore or the mixture of ore and water. Most likely there will be a separate webinar describing the swirl and exactly how it works. We have very accurate measuring results of the toe position. It's scaled in centimeters, so it's very accurate. And the aim of this toe position measurement is try to find a sweet spot where the mill operates as its optimum performance. So in this case, for this mill, if the toe position is somewhere within this area, then we know, or the operators know, that the mill is performing at its optimum. So that is the idea, that you will find your sweet spot where you will have the toe. So how do we find the sweet spot? Well, you need to have a tuning period. And basically what you do is that you run the mill with different inlet feeds, outlet discharge. You keep track of the motor power and the particle size. And then you correlate this and try to figure out exactly where you have the sweet spot. I hear some noise. Shall we continue? Okay, I continue. So running the mill at the sweet spot will result in maximum throughput, optimized particle size, optimum energy consumption, minimizing the linear wear, and also elimination of the volumetric overload. So I will take that again. Running the mill at the sweet spot will result in maximum throughput, optimized particle size, optimum energy consumption, and minimizing the linear wear, and also elimination of the volumetric overload. It is also important to keep track of the toe position both at the inlet and at the discharge side. So in this case, for example, we have the toe position here for the inlet, and then hopefully outlet, the discharge side, is lower. So that's a typical scenario where the inlet is higher than the outlet. But it's important to keep track of these, and so they're not coming too close to each other, because if they are too close to each other, the mill is not running. I lost it there. You can just cut it after. It's important to have keep track of the inlet and outlet toe position. There are several benefits to monitoring toe position, one of which is to detect mill fault modes. However, the most important benefit is to find the optimal toe position to produce a specific particle size. These results here are from a particle size counter over roughly 3 months. And you can see the average value and the width of the distribution is not optimal. We are here, but we would like to be down here. Using toe position measurements makes it possible to optimize the particle size and distribution. It is clear from the particle size distribution that most of the ore particle is too large. So using a high resolution toe position measurements makes it possible to get closer to the target range. So actually what we want to do is move the majority of the particles down to this size, because then it's, in this case, it's a gold mine, so it's much easier to extract the gold if the particles have a certain size. Now, typically, if you look, this is another way of seeing the same results. You have the particle size here on the x-axis, and you can see that the majority of the particles are in this area, but we would like to be down here. And typically, if you have the high toe position, the particles that you will get out of the mill is larger. If you have a lower toe position, the size of the particles will be smaller. So in this case, you adjust the toe position to have a suitable particle size. Another important thing is to keep track of the conditions of the lifters. We use circular plots from the time signal, and that is representing each impact between the lifters and the charge. And that's a very useful method to identify if some of the lifters are damaged, because then you will easily see that in this circular plot. For example, if this lifter has a damage, the amplitude here, when that lifter or this damaged lifter hits the charge, the signal will be much lower. So it's very easy to identify that in this circular plot. So to summarize, the benefits of toe position: it's very high accuracy of the toe position data. There is a correlation between the particle size and the toe position. It's an early detection of fault modes in the mill. And you keep track of the inlet and outlet toe position to avoid outlet blockage. We detect lifter damage. Very easy installation. Basically 2 vibration sensors and 1 tachometers. And there's no hardware attached to the shell. So that was a very quick summary of the toe position in tumbling mill. And then the next step here is to look at condition monitoring of a tumbling mill. And same mill, just another view of it. And we will look on the drivetrain here, and especially the gearbox here. When it was installed, everything was running nice and smooth, but then suddenly something happened with this gear. and the acceleration values went quite high. And if you look in the spectrums, you will see a very clear gear mesh here related to the input gear here. And if you look in the spectrum, it's a very crisp and clear spectrum showing the gear mesh frequencies with sidebands correlating to that gear. And if you look in the color spectrum overview, you can also see that there is a quite dramatic increase here of the amplitudes. And then after the replacement of the gearbox, the reading drops down. Unfortunately, they didn't have a new spare gearbox, so they had a gearbox that was what has been running for a while. But they installed it, but after about 5 months, they discover a bearing damage in the gearbox. And in this case, it's a BPFO with sidebands, and that was due to a wobbling shaft, so it was quite heavily damaged. And the inner race was also damaged. So this was just a quick example of where you can use the system for both process optimization and condition monitoring. Another application that is very critical is hoists. And we have one case here. It's the drivetrain looks like this. You have an electrical motor, a two-stage gearbox, driving a wire drum like this. And what is interesting here is that there are helical cut gears. And if you look on the loads on this gear, you will notice that depending on the rotation of the drum, you will have a strong axial force in that direction. And when the drum is rotating at the other direction, there will be a force in the other direction. So if you look on this bearing, this spherical roller bearing, already here in November 2014, we could see a rise in the HD enveloping filter 4 readings. And it continued. And then in May, the year after, we could see an HD enveloping filter 3 rising. And then they decided to replace the gearbox in 2017. So it was 2 years and 8 months pre-warning. And here you can see when the readings are high, you have one rotation direction. And when the readings are low, it's rotating in the other direction. So it was expected that, or suspected that there should be a damage on the inner race, something like this. And the gearbox was, this is how the reading looked like just before the replacement. The gearbox box was open up, and when you look on the bearings, there were very, I'll say, nice spalls on the inner race like that. This was a really good examples of very long pre-warning times using the HD technologies. And the bearing was replaced in July 2017, and you can see that after that the readings are nice and low. Here's another case from another mill, but it's quite similar drivetrain, quite similar gear assembly. If you look on that bearing, the readings start to rise in 2016 in May, and then in October the same year the readings are quite high, and they decide to replace the bearings. It was a ball there on the inner race. I would assume that they could have run quite longer with this one, but they decided to change the bearing at this time. Okay, the next one we will look at is belt filters. And what is typical, the example is from a Finnish mine from Yara in Siilinjärvi in Finland. It's open pit mine. And here they are monitoring belt filters. And what is special with these ones is that it's a lot of moisture and low RPM. And it's not only low RPM, the RPM is fluctuating as well. So typically during a data acquisition, the RPM can fluctuate 1, 2, 3 RPMs. And that is quite a lot considering the relation between the RPM and the fluctuations. So the percentage RPM fluctuation is relatively large. This is how it looks like in ConMaster or software. You have green and yellow dots. And they had some problems here, and in 2021 they have 3 bearing replacements, and last year 2022 also 3 bearing replacements, and they have decided to change from ball bearings to spherical roller bearings, and I guess that will solve a lot of problems. However, what I wanted to highlight here is the very crisp and clear results we get. Here is from SBM HD, and we have the max RPM is 20.5 RPM and the minimum RPM is 20.08. Very crisp and clear. Same measuring points, but we look at HD enveloping filter 3. Also very nice, crisp and clear results. Filter 4, same thing. Here we have minimum RPM 20 RPM and the maximum RPM is 21.7. That was the RPM fluctuation during the data acquisition. That's how the bearing looks like. We have another example here, same story, very crisp and clear results from SBM HD. Basically the same kind of results from HD enveloping filter 3. HD enveloping filter 4, same thing, very crisp and clear results. And the last case here where we have loose bearings. You can see very increased shock pulse readings, different measuring technologies, SBM HD, HD enveloping filter 4 and filter 3. And that's how the bearing look like. Okay, then we go for the last example where we also have a combination of condition monitoring and process optimization, but I will only cover the process optimization part. And that's vibrating screens. Here we have the side view of the vibrating screens with the feed here and the discharge over here. On each corner we have a triaxial vibration transducer. We have an RPM pickup. And here we have a slow motion film of a vibration screen deck. A shaker screen with poorly synchronized movements over the deck can cause non-uniform ore distribution, causing non-optimal function. And if you look for the outlet here, bigger ore particles are recirculated. If smaller ore particles suitable for the next process steps are recirculated, it leads to lower throughput. So all the correct size particles should not go for another turn in the mills. Here we can see the screen from above. You have the feed side here, the discharge. You have the feed direction like this. You have the left feed, the right feed side, the left discharge, and the right discharge. And we have developed a dashboard that's showing the elliptical motion in each corner. We also measure the side movements, but that's not displayed in this example. And in this dashboard, we have a reference line for the optimum throw direction. And the optimum throw direction can vary from vibrating screen to vibrating screen. So, of course, this can be changed for different angles. So if you look on the left feed corner here, we can look at the elliptical movement of that corner. And you can see that this corner moves very much in line with the reference line. And we can look at the maximum throw amplitude, in this case 4.7 millimeters. And there is also orbit ratio, meaning that the relation between the amplitude and the width of this orbit. If we look on the other corner, the right feed corner, the signal looks slightly different. It has another throw amplitude, and the orbit ratio is slightly bigger. If you look on the left discharge corner, the angle is slightly different. We have 4.2 millimeters maximum throw amplitude, and the orbit ratio is 6.5% in this case. And in the last corner here, it looks something like that with a throw amplitude of 3.7 millimeters and 8.5% orbit ratio. And then if you look on all four corners at the same time, you can see that they are not the same. They're not moving exactly in the same way. What is acceptable can be different from screen to screen, but at least we measure it and then you can adjust it to have maximum throughput. So to optimize the throw behavior of the screen will lead to maximum throughput. So the benefits, well, detection of unfavorable screen condition, such as non-symmetrical screen movement, excessive energy consumption, spring problems due to screen overload, mechanical stress, and also process capacity losses. Okay, that was end of the vibrating screen case story. That's all. Thank you very much for listening. And if you want to know more, please contact your local SBM distributor for more information. Thank you very much.
As a thank you for attending WOW 11, we are pleased to provide you with a 50% off your conference pass to the CBM and Reliability live training conferences happening in Mexico, the 17th of August, and Australia, November 14th through the 16th. You can use code WOW50 and reserve your seat to take advantage of this discount. These events will include certification training opportunities, hands-on workshops, and case study sessions. You can visit MobiusConnectConference.com to learn more about these live and in-person events. You'll also find the link to register in the follow-up email after this webinar. And thank you again, Hakan, for your time and awesome presentation. And on behalf of the entire team of Mobius Connect, thank you to our wonderful audience for joining us today. Coming up next, we have Misalignment and Shaft Preload and Turbo Machines by Sala Atia, Wednesday, July 26th from 5 to 6 a.m. If you haven't signed up already and would like to attend, please visit the Mobius Connect LinkedIn page for the registration link. Just as a quick reminder, look out for an email from us containing the on-demand version of this session and your certificate of attendance. And if you are interested in engaging with other industry professionals or would like to participate on the industry's live feed and forums on Mobius Connect, you can visit MobiusConnect.com to create your free profile and be sure to follow us on social media at Mobius Connect to stay up to date with the latest community happenings. If you have any questions, you can email the Mobius Connect team at info@mobiusconnect.com. Again, thank you for joining us. Have a great day. Please stay safe, and we'll see you next time.